In this video, we will discuss the concept of performative modeling. The concept of performance is closely tied to the concept of evaluation. Performance is an evaluation of a process. Such a process can be any spatial task, action, or operation. High performance means that the process scores well. Low performance means that it scores badly. A spatial model can be a container for many different types of processes. These processes can all be evaluated. In the example, we are evaluating the process of viewing the canal for an apartment. We are evaluating my apartments in the spatial model. The spatial model itself can also be evaluated. In the example, we can evaluate the model based on the percentage of apartments that get a view of the canal. If the model is of a proposed design, then the design can be evaluated. Performance criteria are any set of criteria that can be used to evaluate a process. Examples include daylight, solar radiation, energy, views, and so forth. For each criteria, specific requirements are specified, depending on the aim. Take solar radiation as an example. In some cases, the aim may be to minimize solar radiation, while in other cases, the aim may be to maximize it. They may also have specific ranges that are required. In the tropics, designers will typically want to minimize solar radiation entering a building. But for a photovoltaic facade, designers will want to maximize it. Designs can be evaluated based on their performance. In performance-based design, many design options are typically generated. All these options can be evaluated for the same set of performance criteria. The design options can then be compared to one another based on the performance scores. The predictions are for future performance assuming the design is actually constructed. Computational models can be used to calculate such predictions, using various methods. We will discuss two methods: detailed simulations and simplified performance indicators. Performance-based design exploration is an iterative process of exploring design options. The aim is to reveal the complex relationships that exist between spatial form and performance. We can think of it in terms of two cyclical loops. In the ideation loop, the designer comes up with design ideas and strategies. In the exploration loop, the designer then generates and tests multiple options based on these ideas and strategies. In the ideation loop, both the problem and solution can be manipulated. So design requirements may be specified and performance criteria may be defined. In the exploration loop, the requirements and performance criteria are frozen, and many possible design options are being investigated. It is also possible to automate some parts of the exploration loop. Using optimization algorithms, it becomes possible to automatically search for design options that perform well. Optimization algorithms will use some kind of search mechanism to discover new improved designs. An example is an evolutionary optimization algorithm. A population of designs is evolved through multiple generations. Each generation, designs are generated and evaluated. And through a process of survival and reproduction, the performance will gradually improve. Computational models can be used to predict performance for specific criteria. One approach is to use a detailed simulation program. Such simulations can be highly complex. They typically require specialized software. Two examples are the Radiance tools for lighting simulations and Energy Plus for thermal simulations. Both these programs are free and open source. We will briefly discuss these programs. Radiance is an advanced suite of tools for performing lighting simulations. These tools can be used to perform highly detailed lighting simulations that can take many hours to complete. The inputs to the simulation require various datasets. The spatial model is described the scene to be simulated. The specific spatial representation is required that focuses on the requirements of lighting simulation. This is a text-based representation called a RAD file. Various detailed settings can be specified. Often, simulation settings result in a trade-off between simulation accuracy and simulation speed. For example, one key setting is the number of bounces for each ray of light. This will limit how many times the light will bounce around the scene before being discarded. More bounces will result in greater accuracy, but will also be exponentially slower. The image shows an interior lighting simulation, showing lux values. In some cases, the process being simulated dynamically varies as time progresses. In such situations, dynamic simulations are required. Examples include the simulation of fluid dynamics and thermal dynamics. In a dynamic simulation, the simulation proceeds in discrete time steps. The state of the simulation in each time step depends on the previous time step. The image shows one time step from a simulation of a typhoon. The simulation duration is 48 hours. The Energy Plus program is an advanced dynamic thermal simulation program. The thermal simulation proceeds in discrete hourly or sub-hourly time steps. The program is commonly used to simulate energy consumption of buildings. It can simulate many different systems, including heating, cooling, lighting, and ventilation. The inputs to the simulation again consist of various datasets. But these datasets are all different from those required by other simulations, such as radiance. This means that if we want to run simulations with both Energy Plus and radiance, we would need to maintain multiple different representations and datasets. This can become very complex, especially when multiple design options are being explored. In this case, the spatial model needs to be converted to the Energy Plus representation. The representation focuses on the requirements of thermal simulation. It is a text-based file called an IDF file. Along with the spatial model, many other settings need to be specified to describe the building materials and systems. Spatial simulation programs all have their own custom spatial representations. These representations are designed to contain only the data required for the simulation. Even though the simulations may be very detailed, the spatial models are usually highly simplified. For example, for Energy Plus, a simplified surface model is required. The detailed form and structure of the building is not represented, as it is not relevant for a thermal simulation. The thickness of surfaces such as walls and slabs are also not modeled. Instead, building surfaces are defined using polygons. The material properties are defined as attributes attached to the geometric entities. The image shows such a model. Simulations such as Radiance and Energy Plus require a lot of detailed data. And they can be very slow to execute. Instead of running detailed simulations, performance indicators can be used. In this course, we will be using various types of performance indicators. Performance indicators are simplified calculations that require less data and are faster. They are usually not dynamic, and therefore can be executed in a single time step. However, they are of course less accurate. Next, we will have a look at two types of analysis commonly used for performance indicators. They are network analysis and ray casting analysis. Network analysis is a type of analysis performed on spatial networks. A network is an abstract data structure consisting of a set of nodes connected by edges. Network analysis can then calculate various properties of such networks. For example, shortest paths can be calculated through the network. The image shows a network where various shortest paths are highlighted by extruding the edges. The paths all start at the same node and end at various other nodes in the network. Ray casting analysis fires numerous rays into space. If the rays intersect with surfaces in the spatial model, then the points of intersection will be returned. If the rays do intersect anything, then no points of intersection are returned. The results from ray casting can be used to analyze many types of spatial properties. Next, we will give a few examples that use ray casting as an analysis method. Here, we show 3 examples of performance indicators using ray casting. All 3 indicators are calculated for the windows on blocks of high-rise apartments. The indicators are calculated by analyze the center point of each window. The first is a solar radiation indicator. It is calculated by casting rays from the window centroid towards the sun paths for specific latitude. The second is a scenic views indicator. For this indicator, the canal is assumed to be a scenic view. It is calculated by casting rays from the window centroid towards the canal. The third is an unobstructed view indicator. The indicator calculates the openness of the horizontal view in front of a window. It is calculated by casting rays from the window centroid outwards in a horizontal fan shape. Ray casting analysis can also be used to generate continuous gradients over a surface of analysis. For this type of analysis, a grid of polygons is created in the surface to be analyzed. Ray casting is then performed for each cell in the grid. In the images, 3 examples are shown. The first calculates solar radiation on the ground plane. Rays are cast from each grid cell towards the sun paths. The second calculates daylight on the inside of a fully glazed building. Rays are cast from each grid cell towards the sky dome. The third calculates solar radiation on a set of windows. It is similar to the previous examples. Rays are cast from each window centroid towards the sun paths.